Hello viewers, in my last lecture on reactive methylene compounds, I had discussed tautomerism in ethyl acetoacetate in great details. Today I shall be discussing synthesis of ethyl acetoacetate from ethyl acetate with you. So on your screens now you can see the structure of ethyl acetoacetate. In ethyl acetoacetate, we have a methylene group which is reactive in nature and it is indicated by red on your screens. This group, the methylene group, is sandwiched between two electron withdrawing groups. One is the aceto group and other is the ester group. Therefore, the hydrogens of this methylene group are acidic in nature. That is, they will undergo deprotonation easily. Now let us look into the IUPAC name of this molecule. I would like to explain it to you. It is ethyl 3-oxobutanoate. Why so? See, basically you think that this is an ester and this ester is ethyl butanoate. So when we are saying it is ethyl butanoate, we do the numbering of the molecule from right hand side starting from the carbonyl carbon. So carbonyl carbon is the first carbon, methylene carbon is the second carbon, again the carbonyl carbon is the third carbon, and methyl carbon is the fourth carbon. So this molecule is now an ester. So the root name will become ethyl butanoate. But what we find that at the third carbon on the main carbon chain we have a carbonyl group, and this is named as oxo because this is here coming as a substituent. So this molecule is named as ethyl 3-oxobutanoate. The main ester is ethyl butanoate, and at the third carbon of the parent chain we have the oxo group, so we name it as ethyl 3-oxobutanoate. Coming to the synthesis of ethyl acetoacetate, I would like to discuss the preparation by Claisen condensation. So, but before I start with the preparation of ethyl acetoacetate, I would like to discuss what is Claisen ester condensation and what are the salient features of this reaction. Base catalyzed condensation of an ester containing alpha acidic hydrogen atom with a molecule of same ester or a different one to give beta keto ester is known as Claisen ester condensation. So that means, what is the basic reaction? As you can see on your screens, two ester molecules react together in presence of a strong base to give a beta keto ester. Now these two ester molecules can be same, as we can see in the case of general Claisen condensation reaction, which are ethyl acetate. So when we look into ethyl acetate, what we find that the CH3 group, which is next to the functional group, is the one which has the alpha carbon, and the hydrogens attached to this alpha carbon are alpha hydrogens. Since this methyl group is attached to an electron withdrawing ester group, the hydrogens of this methyl group are acidic in nature. That is, they can be easily removed by a strong base to form a enolate ion. That is why we are saying that we need here a enolizable ester which will result in the formation of enolate ion, which will then act as a nucleophile. And in the product, what are we getting? We are getting a beta-keto ester. Now, what is a beta-keto ester? If you look at the structure of the beta-keto ester, we find the carbonyl group of the ester moiety is the first carbon. And the methylene group, which is next to the functional group, is known as the alpha carbon. The carbonyl group, which is next to the methylene group, is the beta carbon. So what do we find? That at the beta position, we have a keto group. And the parent is an ester. So we have an ester in which the keto group is at the beta position. Therefore, we say that in Claisen ester condensation, two esters which have an enolizable hydrogen react to form a beta keto ester. Either both the molecules can have enolizable hydrogen, or the basic condition for Claisen condensation reaction to take place is that at least one of the ester should be enolizable. For example, you can see on your screens, I have shown you a structure of methyl acetate. In methyl acetate, the hydrogens of the methyl group are enolizable. That is, they are enolizable. That is, we will get a enolate ion from here. Whereas, if you look into the structure of phenyl acetate, what we find here that the phenyl group does not have alpha hydrogen in it. Since it does not have alpha hydrogen in it, this is a non-enolizable ester. So when both of the esters are different, one of them is enolizable, the other is not enolizable, we will say a crossed Claisen condensation has taken place and we will get one product. Now, if supposing we go on to a mechanism reaction in which both the molecules of esters are enolizable, they have enolizable hydrogens, or they are enolizable, then in that case we will get 4 products. And that means that reaction from point of organic synthesis is not practical, because separating these 4 products would be very cumbersome. So if we are carrying out the reaction between 2 different esters, one of them is enolizable, the other is not, we will get 2 products. And if we want to just get one product as a major product, then in that case, the concentration of the non-enolizable ester should be more. Second point you have to remember, that carrying out reaction between 2 enolizable esters will give us 4 products, which will be difficult to separate. So here again I have shown you that if we carry out the reaction between phenyl acetate and methyl acetate, which is an example of crossed Claisen condensation reaction, or we can say it is an example of crossed mixed Claisen condensation reaction. In this case, we are getting one major product, which is a beta keto ester. Now we go on to what should be the nature of the base. So if we talk of the nature of the base, we should not take hydroxide ion as a base. The reason being that this molecule in Claisen condensation could also bring about saponification of the ester. So that is not a very wise idea to use hydroxide ion as the base in this reaction. we can use sodium alkoxide. We can carry out the reaction with sodium alkoxide, in which case the alkoxide is acting as a base, which is a very good reagent to bring about Claisen ester condensation. But the point to be kept in mind here is that the base which we are using to bring about the reaction should be same as the leaving group in the ester. Otherwise, what will happen? We will have transesterification of the reaction. Let me illustrate this by taking an example of methyl acetate. That is, if we carry out the reaction of methyl acetate with ethoxide ion, this ester can undergo transesterification to form ethyl acetate. So what I mean here is that this ethoxide ion will act as a base and help in generation of the enolate ion. But at the same time, it can also undergo transesterification with methyl acetate to form ethyl acetate. Now these two ester molecules, that is methyl acetate and ethyl acetate, will react with ethoxide ions to give us a mixture of beta-keto esters. So this will be the drawback of the reaction. So what you have to keep in your mind, that the base alkoxide ion which we are using should be same as the leaving group, which will depart from the enolizable ester. So what we find here is that, as you can see on your screens, that when we carry out the reaction of methyl acetate with ethoxide ion, it results in the mixture of two beta-keto esters, so the yield of the reaction will be low. So now, what do we have to keep in mind? We have to keep in mind, while we are carrying out Claisen ester condensation, that is, one of the ester should be enolizable, which we say is the donor ester, and the other ester, we can say, if it is not enolizable, we say it is an acceptor ester. And the second thing that we have to keep in mind is that the alkoxide ion which we are using as a base should be same as the one which will depart from the ester. So that means now in this case we can justify that when we are carrying out the condensation reaction of ethyl acetate to prepare ethyl acetoacetate, in that case we are taking sodium ethoxide as the base. That is, in that case the base is ethoxide ion, and the alkoxide ion which will depart from ethyl acetate is also ethoxide. So this is what you have to keep in mind. So that means now when we are carrying out the preparation of ethyl acetoacetate, we will prepare it by heating ethyl acetate with sodium ethoxide in ethanol, followed by acidification. For this, in laboratory, a mixture of ethyl acetate and sodium ethoxide is heated at 78 degrees Celsius for 8 hours. The mixture is cooled and acidified by slow addition of acetic acid or dilute HCl. The oily layer is separated and dried. So on your screens, now you can see the reaction between two molecules of ethyl acetate. So in this simple reaction, what I have done, we have shown that the ethoxy group, this is the leaving group, and the proton from the other ester, which is acting as which has an enolizable methyl group in it, or enolizable hydrogen, is being removed as ethanol, and what we are getting here is ethyl acetoacetate. This I have explained in the beginning of the lecture, that the methyl group here is the alpha group. It is the alpha carbon, and the hydrogens attached to it are the alpha hydrogens. These hydrogens are acidic in nature, so they are enolizable, that is they can be deprotonated easily, that is they can be removed easily with a strong base, resulting in the formation of a enolate. And when we talk of beta-keto ester, that also I have explained. Why is ethyl acetoacetate a beta-keto ester? Because in that the keto group is present at the beta position. So when a reaction is carried out between two molecules of ethyl acetate in presence of sodium ethoxide and ethanol, we get this reaction will then be followed by acidification. You will get ethyl acetoacetate and ethanol. So what is the mechanism of the reaction now? Ethoxide ion from sodium ethoxide attacks the ethyl acetate to form enolate anion and ethanol. So why does this happen? Because the carbon atom which is adjacent to the carbonyl group, you know, is the alpha carbon. And when this alpha carbon, the hydrogens attached to this alpha carbon are enolizable. Why is it so? Because the carbonyl carbon will pull the electrons towards itself, as a result of which the bond between the carbon, alpha carbon and the hydrogen, alpha hydrogen will be weakened, and these hydrogens can be deprotonated easily. That is, they are said to be enolizable, and they will result in the formation of enolate ion. So when ethyl acetate is treated with a strong base, deprotonation of alpha carbon of ethyl acetate occurs, resulting in enolate. So as you can see on your screens here, the ethoxide ion from sodium ethoxide pulls the protons towards itself, resulting in formation of ethanol, and in the process enolate anion is formed. Now this enolate anion is resonance stabilized because we have a negative charge on alpha carbon, and then in conjugation we have a carbonyl group. So the negative charge is now spread over this methylene carbon and over the oxygen of the carbonyl group, resulting in two resonating structures. Next point that you have to keep in mind, that these enolate ions are good nucleophiles. Why are they good nucleophiles? Because they can form bonds with carbon. So what you have to remember now here is ethoxide ion is acting as a base because it is abstracting a proton, and enolate ion is acting as a nucleophile because it is making a bond with the carbon. Next point that you have to remember, that when this enolate ion forms a bond with the carbonyl carbon of the second molecule, that means a new carbon-carbon bond is being formed here. So now what will happen? This enolate carbon will attack the electrophilic carbonyl carbon of the second molecule of ethyl acetate. Right? So when the nucleophile forms a new bond with the carbonyl carbon, the carbon-oxygen pi bond breaks, and it will result in the formation of tetrahedral intermediate. So this again I have shown on your screens, that this is an addition reaction. In this addition reaction, the enolate ion, as you can see on your screens clearly, which I have shown with an arrowhead, is making a bond with the electrophilic carbonyl carbon, and oxygen being more electronegative pulls the pi electrons towards itself. That is, the bond between carbon and oxygen is breaking, and it results in the formation of tetrahedral intermediate. Now what happens in the next step? In the next step what happens is, the negative charge on the oxygen of the tetrahedral intermediate can reform the CO pi bond, and in doing so we break the CO sigma bond. That is, the bond between the carbonyl carbon is being formed and the sigma bond is being broken between the carbon and the alkoxy group. And now this will result in a beta keto ester, and then ethoxide group will be the leaving group. So what you find here is what I was trying to explain, that this negative charge which is here will come back and it will make a pi bond here. So when it makes a pi bond here, what you find that the valency of carbon is 5, and when the valency of carbon is 5, that is not possible, and this is the leaving group, this ethoxide ion is the leaving group. It will take this bond, the sigma electrons, and this will break, and it will form a ethoxide ion here, and what we'll get here is ethyl acetoacetate. But now what you have to remember, that together step 2 and step 3 together make nucleophilic acyl substitution reaction. You know this, that esters, acid and acid derivatives undergo nucleophilic acyl substitution, which is different from nucleophilic substitution reaction. How? In nucleophilic acyl substitution, first addition takes place across the carbonyl group, resulting in tetrahedral intermediate, and then there is elimination of the leaving group. So that means step 2, in which the enolate ion is making a bond with the electrophilic carbonyl carbon, and the second step in which the ethoxide ion is departing, both these steps together will constitute nucleophilic acyl substitution. And now in these two steps, in the elimination reaction, you have to keep in mind what is happening. The ethoxide ion of the acetate gets replaced with CH2COOC2H5 group, resulting in the formation of ethyl acetoacetate. But the point to be noted here is that in this process, a strong base is being eliminated, which is your ethoxide ion. So now a question is there. We've already got ethyl acetoacetate. What is the need to bring about acidification? As I've said, the point to be noted here is that ethoxide ion is being eliminated as a base, and since ethoxide ion is being eliminated as a base, what will happen? It will deprotonate the hydrogen of the methylene group, right? So what will happen here now, that this will, the ethoxide ion here, as you can see on your screens, will abstract a proton from the methylene group, resulting in formation of ethanol, and the sodium will make a bond between with the carbon, resulting in the formation of sodium salt of ethyl acetoacetate. Now you have to keep in mind, now if you look into the second structure, there we have indicated methylene group, the carbon of the reactive methylene group, we have put a minus sign there, and on sodium has a positive charge. So what is this? This is existing as a ionic molecule, ionic group here. That is, we are not making a bond here. So what you have to remember is CH minus Na plus. Like if I talk of sodium chloride is an ionic compound. How do you write it? Na plus Cl minus, clearly indicating the ions. So that is why we are showing here that it is CH minus and Na positive. Since the beta keto ester formed in Claisen condensation is converted to corresponding enolate ion by the base, in order to isolate the beta keto ester when the reaction is complete, the reaction mixture needs to be acidified. That is the need here. Now see, as you can see here on your reactions, I have shown both the reactions together so that there is no confusion. In the first case, what we've said, that we are getting sodium ethoxide, right? Now this ethoxide will abstract a proton from the molecule which is on the left hand side, and sodium will react with it, resulting in the formation of sodium salt. But we do not need this sodium salt. What do we need? We want to prepare ethyl acetoacetate. So what do? We carry out the acidification of this reaction. And when we carry out the acidification of this reaction, say with dilute HCl or with dilute acetic acid, this Na sodium is removed. As if we are taking HCl, it is removed as NaCl, resulting in the formation of ethyl acetoacetate. So this is how it is prepared, and this is what is the mechanism of the reaction. So let me now quickly summarize the mechanism. In first step, sodium ethoxide ionizes to give us ethoxide. This ethoxide now abstracts a proton from the alpha carbon of the ethyl acetate. Now this molecule will now further, when it abstracts the alpha carbon from there, it will now act as an enolate ion. It will react with the second molecule of ethyl acetate, resulting in a tetrahedral intermediate. And in the next step, a pi bond will be made between the carbonyl carbon, and the ethoxy group will be given out because it will depart as a leaving group. And in the end, we will have to carry out the acidification of the salt which is formed to regenerate the ethyl acetoacetate. For this, I had consulted books of Behl and Finar, and you can also do so. Thank you.